Okay, the first thing I want to go through on this video is the solution to the last question on the packet that we did on Tuesday night. This question is about a statistics student is interested in the proportion of male students at his school. He samples 180 and he finds that 80 of them are male. And then the question here is, does this provide evidence at the 5% level to suggest that less than half of the students are male? All right, so first step is the null hypothesis. Okay, this is about a proportion, and we want to assume that the proportion here of males is 50%. All right, and then the question is asking, is there evidence to suggest that that proportion is less than 50%? All right, and then here, P represents the proportion of all students who are male. Right. By all, I mean all students at this school. All right, the next thing I want to do is check conditions. The conditions are, it was a simple random sample. All right, the problem says he's interested, he samples 180. All right, we're going to assume that he took that sample as a simple random sample. And then the other condition is that we got to check to make sure that NP and NQ are both big enough. All right, his sample size was 180. We're assuming 50% of the students are male. This is going to give me 90. And then 180 times Q is also going to be 50%. This is 90. Those are both bigger than or equal to 10, so we're okay with those conditions. All right, the conditions guarantee that the sampling distribution of the sample proportion is approximately normal. All right, so we're assuming this is centered at 50%. Standard deviation of this is the square root of 0.5 times 0.5 divided by n. And that's going to give me 0.5 times 0.5 divided by 180. And the square root of that is 0.037. All right, now in our sample, p hat was equal to 80 out of 180. And 80 out of 180 is 44.4%. Okay, so we got a sample proportion of 0.444. All right, we want to know what's the probability that we're going to get a value that's less than that from a simple random sample, an average. All right, so on the calculator then, this is going to be normal CDF again. Our lower bound is negative infinity essentially. We're going to 0.444. The mean is assumed to be 50%, and the standard deviation we found was 0.037. All right, so this probability is going to give me about 6.5%. All right, now the question says, check this at the 5% level. 6.5% you could argue is a small proportion or a small probability, but it is bigger than 5%. So our decision is to fail to reject the null hypothesis. The reason is the p-value is 0.065, and that's bigger than our line in the sand of 5%. All right, and then in words, that means we do not have sufficient evidence to suggest that the proportion of males is less than 50%. Okay, we don't have any evidence to suggest that there's less than 50% boys at this school. All right, now the other part of this says construct and interpret a 95% confidence interval. All right, so that confidence interval is going to look like p hat plus or minus z star square root pq over n. All right, so the p hat that we got here was 44.4%. Plus or minus the z star for 95% confidence is 1.96. And then inside here, we're going to use the p hat and the q hat. So we're going to have 0.444 and 0.5, what is that, 556 divided by 180. All right, so on the calculator, then I'm going to do 0.44 minus 1.96 times the square root, 0.444 times 0.556 divided by 180, and then close that. All right, so we get a bottom value of 37.1% and an upper value of 0.516. Okay, so this is our confidence interval. Then interpret. So the interpretation is I am 95% confident that between 37.1% and 51.6% of all students at this school are male. Okay, and then the other part of this question says, is this confidence interval consistent with our hypothesis test and decision in part A? Remember, we said there wasn't enough evidence up here to suggest that the proportion of males was less than 50%. Right? And if you look at this interval contains 50%. 50% is a plausible value for the proportion of males at this school. So the answer to that question is yes, they are consistent. Okay, because 50% is in this interval. Okay, so that finishes up the packet that we worked on last night in class. Now I want to go through and give you solutions and give you some commentary on the final exam review that I gave you last night. Some of these problems I've got worked out, and some of them I'm going to work out with you. But this first one is about the dogs, and it's as dogs age, diminished joint and hip health may lead to joint pain and thus reduce the dog's activity level. Such reduction in activity can lead to other health concerns. A study is to be conducted to see which of two dietary supplements, okay, we're talking about these two things, we don't have to know anything about those, just that they're two treatments, is more effective in promoting hip health and joint health. Okay, researchers will randomly select 300 dogs from 10 different large veterinary practices around the country. All of the dogs are more than 6 years old, and their owners have given consent to participate in the study. Changes in joint and hip health will be evaluated after 6 months of treatment. Right, then they want to know, is there any benefit to having a control group? All right, remember, a control group is just a group that, or is a group in a study that gets no treatment. All right, so we're going to have some dogs. If we did have a control group, we just have some dogs that we're just going to measure their joint health and see how that changes over time without any kind of treatment. All right, if we've got 3 groups here, one with glucosamine, one with chondroitin, and one with nothing, all we're going to be able to do from this control group is see, is there any benefit to using any kind of a treatment on this one over no treatment at all. All right, so that's what the researchers are going to gain from looking at a control group here. For the second part of this one, they want to know, talking about blocking. All right, now remember, blocking was where we were going to take one characteristic and we were going to split people up according to that characteristic. All right, so maybe that characteristic is males and females, and we're going to block, and then we do 2 separate experiments, one on the males and then one on the females. All right, in this case, they want to know, should we block on the breed of a dog, or should we block on what veterinary clinic they came from? Now, if we think about how those are related to joint health, right, I would imagine that probably the breed is going to be related to the size of the dog, and the size of the dog is probably going to determine the hip problems. Okay, I think that bigger dogs tend to have more hip problems than small dogs do. And if you looked at veterinary clinics, I would imagine that veterinary clinics probably have a variety of sizes of dogs, and I would guess that probably from clinic to clinic, they're pretty much the same in terms of the proportion of big dogs versus small dogs. So I don't think that we would end up getting any more information if we blocked by clinic and did this experiment over and over in each of the clinics. Okay, I think it's more important that we split these up in the size of the dog and then do the experiment within the size of the dog. Okay? All right, so on the second page, this one is about, as part of a 25th reunion, class of '88, at a state university held a reception on campus, and an informal survey the director of alumni collected or developed asked 50 of the attendees about their income. The director computed the mean income of the 50 attendees and found it to be $189,952. In a news release, the director announced, "Members of our class of 1988 enjoy resounding success. Last year's mean income was $189,952. Right, then Part A says, would you expect the distribution of salaries to be skewed left, skewed right, or symmetric? All right, so I'm thinking that 189,000 is a fairly high average salary. And I'm guessing that probably there's a lot of people that are probably in that $100,000 to $200,000 range. But I would guess that probably because that average is so high, there's going to be a couple of people that are probably in the millions or several millions, which would mean that this distribution would be skewed to the right. Okay, and so that's why I'm thinking that this distribution is probably skewed right. Part B says, what would be a statistical advantage to using the median? All right, well, if you remember, the median is just the middle number if they're listed in order. And I think that the mean on this one is going to get pulled to the upper end. I think that the very rich people in this sample are going to pull the mean higher than it usually would be. And then if we talk about the median is just going to be the middle value, and I would guess that probably the middle value here is going to be more representative of the salaries in this group instead of the mean. All right, and then if you look at this Part C on this one, they've got two techniques that they want to use to collect information from these people. All right, the first method is they're going to send out an email to 6,826 members of the class, and they're expecting that they're going to get about 600 back. Okay? Then method two, they're going to send out a simple random, or they're going to select a simple random sample. They're going to call these people by phone, and then they're going to follow up. Because method two will require more time than method one, the staff estimates that they can get a hold of 100 members of the class. All right, so which of the two methods would you select for estimating the average yearly income of all 6,826 members? All right, so I picked method two. All right, now there's a couple things with this. Number one, method one has a bigger sample size. They're expecting 600 instead of 100. All right, but if you imagine, like, this is about 10% of the population, and if you're asking people about their salaries, who do you think is probably going to respond to that question? All right, I think it's going to be the people that have been successful financially and are going to be more likely to respond to this. The people that have lower salaries, I think maybe they're not going to want to respond to this questionnaire. All right, this method two has a smaller sample size, but this is going to be a more representative sample of the population. All right, and so that's why I'm picking number two, is that they're going to keep following up. Now, they may not be able to get a hold of all 100 of these people, but once they do get a hold of them, they really don't have the option of not responding. Okay, so this is really an example of non-response bias that's going to be introduced into this sample if they don't take a simple random sample of people in their population. Okay, so moving on to some of the probability questions. This one is about members of a high school, and we collected information on what class they're in and then how many activities they were involved in. All right, and then I've given you also the totals here in the columns and the rows. All right, so the first question is, what's the probability a student is a senior? All right, well, these are all the seniors up here. There was 125 of them, and there was 575 altogether. So 125 out of 575. And if you want that as a decimal, 125 out of 575, that is about 21.7%. Okay, find the probability a student is a freshman or sophomore. All right, so freshman or sophomore, there was 310 of them out of 575, and 310 out of 575, that is about 53.9%. Find the probability a student participates in less than 2 activities. All right, less than 2 activities means 1 or none. All right, and there was 185 were not in any activities. 170 were in only 1 activity. If you add those up, 185 plus 170, that gives me 355 out of 575. And 355 divided by 575, that is 0.617. Find the probability a student is a sophomore and participates in 1 activity. All right, there are 50 of those that are sophomores in 1 activity. So 50 out of 575. And that is about 8.7%. Okay, find the probability a student is a sophomore or participates in 1 activity. All right, so there's going to be a bunch more of these. Okay, there are 160 sophomores. There are 170 people that participate in 1 activity. Okay, now the problem is that we've counted 50 of those twice, so we're going to subtract 50 of those and then take that out of 575. All right, so 160 plus 170 minus 50 gives me 280 out of 575, and 280 out of 575, that is about 48.7%. Okay, find the probability a student participates in 1 activity, and this is the important word, given that he is a freshman. All right, so there were 150 freshmen, and of those 150 freshmen, those that participated in 1 activity is 45. All right, so 45 out of 150, and that is 30%. Okay, question G is an easy question. Are these disjoint? Student is a freshman, student participates in 1 activity. All right, and the answer is right here. Okay, there's 45 kids that are in both groups. So the answer is no, they're not disjoint. There are some kids that are in both groups. All right, the next one is a little bit more challenging. Are the events the student is a freshman and the student participates in 1 activity independent of each other? All right, so let's call this event F. Let's call this one involved in 1 activity. Let's call that A for 1 activity. All right, and then to show this, what we need to check is the probability of being a freshman the same thing as the probability of being a freshman given that they participate in 1 activity? All right, so this is one way to check it. Probability of being a freshman, well, there's 150 freshmen out of 575. And then I want to check to see if that's the same thing as the probability of being a freshman given that they're in 1 activity. All right, well, there's 170 people that are in 1 activity, and of those 170, 45 are freshmen. Okay, 150 out of 575 is about 26%. 45 out of 170 is about 26.4%. Okay, this is actually 26.1%. All right, I think we could probably argue that, you know what, those aren't too far apart, and this was a sample. All right, so I would say that you know what, these two events may be independent of each other. Knowing that a student is involved in one activity doesn't change the probability that that student is a freshman. Okay, now another way we could do this is look at the probability of they're involved in one activity. Is that the same thing as the probability of being in one activity given that they are a freshman? All right, and then one last thing that we could do is we could say, is the probability of being in one activity and a freshman equal to the probability of one activity times the probability of a freshman? Okay, so two other ways we could do that. Are these equal to each other? If the answer is yes, then the answer is yes, they're independent. If this is equal to this, then we can say they are independent. All right, so we just need to pick one of those. And I'm going to say that, you know, theoretically, or I guess precisely, these are not the same number. All right, so I would say they are not independent. All right, now the other problem is they're pretty darn close. All right, if these two numbers were exactly equal to each other, I would say for sure they are independent. All right, so I think you could really argue this one either way. They're not exactly the same number, but they're pretty close. All right, I think on the final exam, if I give you the same kind of question, they're either going to be exactly the same number or they're going to be a lot different. All right, and I think that that's probably more realistic of a question. All right, moving on to the next page. All right, this is about airline travel. You know, on airplanes, if they've got, you know, in this case, they've got 38 passenger seats on an airplane, all right, they will actually sell more tickets than they have seats. And the problem is that sometimes you end up with some people that show up that don't get a sit on the plane. All right, and then you've also got the case where if they sold exactly 38 seats, there would be some people that wouldn't show up and they would just end up with empty seats. So what the flight or the airlines bank on is that some people are not going to show up, but there will be some extra people that are there that will be able to take that flight. So that's the idea of this problem. So airlines routinely overbook flights when they expect a certain number of no-shows. An airline runs a commuter flight from Washington to New York on the plane that holds 38 passengers. Past experience shows that 41 tickets are sold, then the probability distribution of the number who actually show up for the flight is as shown in the table. All right, so assume that 41 tickets are sold. There are 38 passenger seats on the flight. What's the probability that all passengers who show up for the flight will get a seat? All right, so I'm going to call this X up here. X is the number of passengers. All right, so what I'm looking for here is, what is the probability that X, the number of people show up, all right? So in order for everyone that shows up to get a seat, that means that we didn't have these extra people show up. So it's the probability that X is less than or equal to 38. All right, so this is the probability that X is 36, plus the probability that X is 37, plus the probability that X is 38. That's going to give me 46% plus 30% plus 16%. And that's going to give me, what, 92%? Okay, so there's a 92% chance that everybody who shows up gets a seat. Okay, and that's fairly high, and that's what the airlines kind of want. All right, then the part B on this one is, what's the expected number of people who show up for this flight? All right, so this one is, you've got a formula that says you're going to take 36 and multiply it by 0.46. You're going to take 37 and you're going to multiply it by 0.30. And you're going to take 38 and you're going to multiply it by 0.16. And you're going to keep doing that until you get to 41 times 0.01. All right, so 36 times 0.46 plus 37 times 0.3 plus 38 times 0.16 plus 39 times 0.05 plus 40 times 0.02 plus 41 times 0.01. All right, this gives me 36.9. Okay, 36.9 is the expected number of people that are going to show up for this flight. Okay, and then that is a problem that you can also do on the calculator, but doing it this way I think is just as fast. All right, number 5 is a fair die is rolled 8 times. Let x be the number of 6s rolled. All right, so this x is going to follow a binomial distribution with n equals 8 and the probability of a success. Okay, this is rolling a fair die, so the probability of a success is going to be 1 out of 6 that we're going to get a 6. Okay, find the probability that 2 6s are rolled. All right, so in a binomial setting, this is the probability that x is exactly equal to 2. All right, now you could do this with the binomial PDF, or you can just do this by hand, but this is going to end up being 8 factorial divided by 2 factorial times 6 factorial, 1/6 raised to the 2nd power, and 5/6 raised to the 6th power. All right, if you punch all that into your calculator, you're going to get let's see, 8. You're going to end up getting the answer to this to be about 26%. Okay, find the probability that more than 3 6s are rolled. All right, so the probability that x is greater than 3, well, this is really the same thing as the probability that x is less than or equal to 2. All right, there's 2 ways that I could do this. One is I found the probability of exactly 2. I could also add the probability of none plus the probability of 1, and that would give me the total answer. All right, but I want to show this one on the calculator. So this is going to be a binomial CDF. The number of trials is 8. Probability of a success is 1 out of 6. And I want to go up to and including 2. Okay, and I want to find the complement of that. Okay, so greater than 3 means same thing as less than or equal to 2 is complement. All right, so if I do 1 minus binom CDF, 8 trials, probability of success is 1 out of 6, and we want to go up to and include 2. All right, so we're going to end up with about 13.5%. Okay, then the last question is, would it be unusual to roll more than 3 6s? All right, well, here's the probability. If something happens 13.5% of the time, are you surprised? I would say no. 13.5% is a fairly high probability. Okay, it's a fairly likely occurrence. Okay? All right, next page. Suppose that the time it takes a student to finish a 50-item test is approximately normally distributed with a mean 60 and a standard deviation of 12. What proportion of students take more than 75 minutes to complete the exam? All right, so I'm thinking about a distribution that looks like this. The mean is 60, the standard deviation is 12, and I want to know what's the likelihood that it's going to take more than 75 minutes. All right, this is just a normal CDF problem. So the second bars, normal CDF, we're going from 75 to something big with a mean of 60 and a standard deviation of 12. Okay, we end up with about, this probability is about 0.106. Okay, so about 10.6% chance of that happening. What proportion of students take less than 51 minutes? All right, so same kind of distribution. 60 is the mean, standard deviation is 12, and we're looking at less than 51 minutes is going to be everything on this side. All right, so again, normal CDF. The lower value on this one's going to be like negative infinity up to 51, the mean of 60, and a standard deviation of 12. And we end up with about 22.7%. Okay, How long would you expect to wait for before 90% of the students are finished? All right, so the question then is, what is this number where we have 90% on this side, and again the mean is 60 and the standard deviation is 12. All right, so this one is set up for a normal CD or an inverse normal. We're looking for the 90th percentile. The mean is 60 and the standard deviation is 12. Okay, so we end up with about 75.4. Okay, so about 75.4 minutes is how long we'd have to wait for 90% to be done. And notice we actually kind of got that number up here in the first question. What proportion will take more than 75 minutes? Well, a little bit more than 10%. Well, there's going to be a little bit more than 10% here as well. Okay, a random sample of 16 students. What's the probability that their mean time will be less than 55? All right, so now we're looking at a sampling distribution of a mean. We'd expect the average there to be 60 again, but the standard deviation is going to be not 12, it's going to be 12 divided by the square root of 16. So 12 divided by 4, that's going to give me 3. All right, and then we want to know what's the probability of being to the left of 55. All right, so now we do normal CDF. Negative infinity to 55, mean of 60, standard deviation now is 3. Right, we end up with about 4.8%. All right, so that's a sampling distribution problem. This isn't just one kid now. This is the average of 16 kids. Okay, I would definitely know how to do these kinds of problems, and I would really encourage you to draw the picture and use the calculator. All right, you can also use the table that you have, but you'd have to convert everything to z-scores first. Okay. All right, next one, 7. Suppose that 28% of all vehicles registered in Lancaster County are red. A simple random sample of 50 vehicles is drawn. Let X be the number of red vehicles in the sample. All right, what's the mean? All right, well, this is, again, a binomial setting. The mean is equal to n times p, and n in this case is 50 times 28%, and that's going to give me 14. Okay, the standard deviation is the square root of NPQ. This is going to be the square root of 50 times P is 28%, and Q then would be the complement of that is 72%. All right, so square root 50 times 0.28 times 0.72. That gives me 3.17. Okay, I'm going to call that 3.175. Okay, and then would you be surprised to get more than 16 red vehicles in a sample of 28? All right, well, if we think about 28, all right, we got 28 vehicles. We want to know, is it unusual to get 16 or more? All right, well, we're expecting 14. And if we add 2 standard deviations to that, okay, we got 14 plus 2 times 3.175. Okay, that puts me at 20.35. Right, this is 2 standard deviations above the mean. 16 is well below that. All right, so I'm going to say, no, I'm not surprised. 16 is just a little bit more than 14, and actually, in terms of standard deviations, it's within 1 standard deviation, so I'm not surprised at all. Okay, number 8. Vehicles registered in a certain county of South Carolina have plates that begin with 4 letters followed by 2 numbers. For example, 4 letters followed by 2 numbers. How many different plates are possible, assuming that the letters can be repeated? All right, so I'm thinking something like this. We've got 4 letters, and then we've got 2 numbers. The number of letters that could fill this spot would be 26, 26, 26, 26, and then the number of digits here would be 0 to 9 is actually 10 digits and 10. Right? Counting principle says just multiply all these together. Right? So we're going to get 26 raised to the 4th power times 10 times 10 is 100. Right? We're going to end up with that many different plates possible. All right, so what is that? 45,697,600. Okay, that's a lot of different license plates that could be made using this method. Okay, I'm sure that probably some of those methods are not going to allow some certain four-letter words. All right, but let's assume that they are, that some of those words are included in this group. All right, so how many different plates are possible if the letters can't be repeated? All right, so again, we're going to end up doing a lot of multiplication here, but these numbers are going to be a little bit different. We could use 26 different letters to fill that first spot, but if they can't be repeated, we've only got 25 left here, and 24 here, and 23 here. We can fill this first spot with 10 different digits, but then they can't be repeated, so there's only 9 that can be filled in that last spot. So again, 26 times 25 times 24 times 23 times 10 times 9, and that gives me a lot of plates also. That's 32,292,000 plates. All right, so quite a few less than we can have up above. If we can't repeat the digits, we're going to end up with fewer license plates. Okay, I would still say that probably 32 million people, probably not that many people live in the county in South Carolina. Okay, so they're probably not going to run out of license plates for people. All right, then the last part of this is getting into the very last thing that we talked about in class, and that was confidence intervals and hypothesis tests. So this one is the three-point basket was introduced into high school basketball in 1987. Officials were concerned about how it would affect the scores. They collected scores from the entire 1986 season and found the mean was 57 and standard deviation was 10. They sampled 35 scores from the 1987 season and found that the mean was 60 points. Assume the standard deviation remained unchanged. Construct a 95% confidence interval for all points scored in every game in 87. Now remember that these 35 are just a sample of those scores. All right, so again, our formula looks like this. X bar plus or minus Z star sigma over the square root of n. X bar was 60. Plus or minus 95% confidence is 1.96 for a Z score. Sigma was 10 divided by the square root of 35. Okay, the lower boundary on this one is going to be 60 minus 1.96 times 10 divided by the square root of 35. And we end up with 56.69. And the upper bound is 63.31. All right, then, does this sample provide sufficient evidence at the 5% level to suggest that the mean number of points scored in 87 is greater than 57? All right, so if you look at it up here, 57 is in this interval. My guess is that we're going to fail to reject. 57 is a plausible value. All right, but this one is really asking us to go through the steps. All right, so we're going to assume that the mean really is still 57. The alternative we want to know is it greater than that? Okay, conditions. Okay, simple random sample, it said it in the problem. Okay, it doesn't say that these scores were normally distributed anywhere, but our n is bigger than 30. Okay, which guarantees that our sampling distribution is going to be approximately normal. Right, and we're saying that the mean for this distribution is going to be 57. The standard deviation for this, now again we're talking about means, is going to be equal to 10 divided by the square root of 35. Right, so 10 divided by square root 35, that gives us 1.69. Okay, our sample mean was 60. And we want to know what's the probability that we're going to get a sample mean of 60 or more. All right, so our p-value is going to be this probability out here. So again, that's a normal CDF. We're going from 60 to something really big with a mean of 57 and a standard deviation of 1.69. It gives me p-value over here of 0.037 or 38. Okay, that's a small probability compared to 5%, so we're going to reject the null hypothesis. The p-value is 0.038, which is less than 0.05. So we have evidence to suggest that the mean, right, and remember this is for 1987, is greater than 57 points. All right, now if you look up here, it seems like maybe we made a mistake then, because 57's in this interval. All right, but actually we haven't really made a mistake. We're 95% confident that the true mean is going to be in this interval. Right now, if we think about what's the probability or what's the chances that our interval that we construct is going to miss the mean, that's 5%. All right, but there's a 5% chance that we're going to miss it on this side or this side. All right, so the likelihood of me getting an interval that is completely above 57% is not 5%. That likelihood is going to be only about 2.5%. All right, and that's why this p-value can be a little bit bigger than 2.5% or less than 5%, and still we're going to reject the null hypothesis. Okay, so these really are not contradictory statements. All right, so I think that, again, if you work through all those problems, and I think that you're going to be pretty well prepared for the exam. Remember that you can also use your calculator. Also, those of you that are using the table, make sure you bring a copy of that table with you. And then everybody received a yellow sheet of paper. You may write out whatever notes you want on both sides of that paper for the final exam. I will be back. I'll be at, down at campus on Tuesday, and I should be there probably sometime between 2:30 and 3 o'clock, and I'll be in that area over by the elevators. So if you have any last-minute questions, please feel free to come over there and meet with me. Otherwise, if you've got any questions about anything that I went through with these packets, let me know. I'm attaching the solutions to this email. And so if you got any questions, just feel free to email me and give me a little bit of time to respond to it. So if you don't have any problems, I'll just see you on Tuesday. All right. Good luck. Have a good weekend. Enjoy the weather.